When we graph the parabola y equals x squared, we can test whether it's a function or not with the vertical line test. When we do the test, we can see that this graph is a function because for every x value, there is only one y value. However, this graph is not a one-to-one function because it does not pass the horizontal line test. This square root function is a one-to-one function because it does pass both the horizontal and vertical line tests. This cubic function is also a one-to-one function, but it is also onto because all of the y values are used in the range. We can use function notation to show that an equation is also a function, which looks like this. Function notation can also tell us when to solve for a variable. For example, if we have f of 2, we can solve for that variable by plugging a 2 wherever there's an x in the function. In this instance, we get f of 2 is equal to 7. We can also solve for compositions of multiple functions, like here we have f of g of x, which can be shown with parentheses. This could also be shown with the composition symbol, which is this little circle. So here we have two functions, f of x, which is equal to 2x plus 3, and g of x, which is equal to x squared. So if we want to find what f of g of 2 is equal to, we first need to find what g of 2 is equal to. So we plug in a 2 for every time there is an x in the equation g of x, which is just 2 squared, which is equal to 4. So g of 2 is equal to 4. Now we just need to find out what f of 4 equals. So we plug 4 in every time there is an x in the equation f of x. So it's 2 times 4 plus 3. And that'll give us 11. So this means that f of g of 2 is equal to 11. We can also do this in the opposite order, which is g of f of 2. This will give us a completely different answer. So again, first we need to find out what f of 2 is equal to. So we plug in a 2 every time there's an x in the equation. So we have 2 times 2 plus 3. And that is equal to 7. So f of 2 is equal to 7. So now we need to find out what g of 7 is. So we plug in a 7 every time there's an x. So it's 7 squared, which equals 49. Therefore, g of f of 2 is equal to 49. We can also perform compositions with variables. Here we have f of g of x. When we have this, we plug in g of x every time there is an x in the f of x equation. So since g of x is x squared, we plug that in to f of x and solve. So we get 2x squared plus 3, which is the result of f of g of x. When we do the composition of g of f of x, we get a completely different answer. So this time we're plugging f of x, which is 2x plus 3, into the g of x equation, which is x squared. So we get 2x plus 3 squared. So when we FOIL this out, we get 4x squared plus 6x plus 6x plus 9. So g of f of x is equal to 4x squared plus 12x plus 9. When we want to find the inverse of a function, for example, f of x is equal to 2x plus 3, we need to switch the x's and y's and solve for y. This is the same as reflecting the graph of the function over the line y equals x. So here we write the equation x is equal to 2y plus 3. Now we just need to solve for y. So we get x minus 3 is equal to 2y. Then y is equal to x minus 3 over 2. Now that we have our inverse function, we need to check it on the graph to make sure that it is still a function. Now that we know that it is definitely a function, we can now replace the y and write f prime of x. F prime of x indicates that this function is an inverse of f of x. Let's do another inverse function. Here we have g of x, which is equal to x squared. So we swap the x and y and get x is equal to y squared. So y is equal to plus or minus the square root of x. This is not a function because it does not pass the vertical line test, so we cannot write f prime of x. The domain of a graph shows which x values are being used, and the range of the graph shows which y values are being used. Here we have g of x equal to x squared. The domain is negative infinity to infinity. Because infinity is not a real point on the graph, we have to write it with parentheses. The range of the graph is 0 to infinity. 0 is a real point, and it is included in the graph, so we can write it with a hard bracket. Infinity is still not a real point, so we still have to use the soft parentheses. So the domain is negative infinity to infinity, and the range is 0 to infinity. We can also write restricted domains of functions. Here we have g of x, which is equal to x squared. We can restrict it by writing negative 2 is less than or equal to x, which is less than or equal to 2. The restricted domain of this graph is now negative 2 to 2. We write this with hard brackets because both of these points are still included in the graph. The new range is now 0 to 4. We can change the restriction so that negative 2 and 2 are not included in the graph. Now the restricted domain is negative 2 is less than x, which is less than 2. This changes both the domain and the range. The new domain of the function is negative 2 to 2. This time though, since they are not included, we use parentheses. The new range of the function is 0 to 4. 0 is still included, but this time 4 is not included, so we use the parentheses. A piecewise function is just a function that's made up of different parts. Instead of having one equation, it has multiple equations, each with their own individual domains. H of x has 5, where x is less than or equal to 1. X squared where -1 is less than x, which is less than 1. And finally, 2x, where x is greater than 1. The domain of this function is -infinity to 1, union 1 to infinity. The range of this function is 0, which is included, to 1, union 2 to infinity. Here we have the rational function f of x. To find the y-intercept, we plug in 0 every time there's an x, and then we solve. So the y-intercept is equal to -2 over -2, which is equal to 1. Next we have the x-intercept. In order to be an x-intercept, a solution on the top must not match a solution on the bottom. Here, only x is equal to -1 is not matched by the bottom. So our x-intercept is -1 and our 0 is -1, 0. Next, we can find the horizontal asymptote. Since the powers on the top are equal to the powers on the bottom, which are both x squared, we then look to the ratio of the coefficients in front of them. So our horizontal asymptote is 2 over 1, which is equal to 2. So it is the equation y equals 2. Next, the vertical asymptote. We look to the bottom of the rational function for any factors that are not matched by a factor on the top. Since the only time this happens is with the factor x plus 2, the equation of our vertical asymptote is x equals -2. The factor x minus 1 is not a vertical asymptote because it is matched with x minus 1 on the top. If we change this graph so that the powers on the top are higher than the powers on the bottom, we have no horizontal asymptote. However, now we need to check for a slant asymptote because the power of x is 1 higher than the power on the bottom. To see if there's a slant asymptote, we need to use long division. The top part of the fraction is divided by the bottom part of the fraction. So we put the unfactored form of the top on the inside and the unfactored form of the bottom on the outside. Since there is no power of x squared on the top, we need to put a 0x squared here to hold its place so we can divide. If there is no remainder when we're done dividing, then there is no slant asymptote. So here we get a remainder of 4x minus 4. So the equation of our slant asymptote is 2x minus 2. Open circles occur when a factor on the top is matched by a factor on the bottom. Here we have x minus 1 on the top and the bottom. So we have an open circle at x equals 1. To find the y value of the open circle, we need to find the limit of f of x as x approaches 1, which is the circle. We can now cancel out the x minus 1's on the top and bottom, and then plug in 1 to the rest of the equation. We now get 4/3 as our answer. So our open circle occurs at 1, 4/3. The domain of this function is -infinity to -2, union -2 to 1, union 1 to infinity. The range is -infinity to 4/3, union 4/3 to 2, union 2 to infinity. A function can be even, odd, or neither. Here we have g of x is equal to x squared. To see if it's even, we need to see if g of x is equal to g of negative x. So g of negative x is equal to negative x squared, which is equal to x squared. So g of x is equal to g of negative x, so the function is even. To see if a function is odd, we need to see if f of negative x is equal to negative f of x. Here we have k of x, which is equal to x cubed plus x. First we have k of negative x, which is negative x cubed plus a minus x, which is negative x cubed minus x. Negative k of x is negative times x cubed plus x. When we distribute, we see that negative k of x is equal to negative x cubed minus x. Since these are the same, the function is odd. If f of x does not equal f of negative x, and f of negative x does not equal negative f of x, then the function is neither even or odd. Here we have f of x is equal to 2x plus 3. So f of negative x is 2 times negative x plus 3, which is equal to negative 2x plus 3. Negative f of x is negative 1 times 2x plus 3, which is equal to negative 2x minus 3. Since f of x does not equal f of negative x, and f of negative x does not equal negative f of x, the function is neither even or odd.